An Arctic mountain should not contain the remains of warm-water marine predators. Yet embedded in its limestone layers are teeth built for cutting flesh, vertebrae shaped for fast pursuit, and isotope signatures that only form in sunlit, nutrient-rich seas. The contradiction is not poetic. It is geological fact. This elevation once lay beneath a shallow ocean basin, where energy flowed upward from plankton blooms into bodies designed for speed and violence. Apex hunters moved through water that no longer exists, under temperatures the region can no longer sustain. The rock remembers a food chain that operated efficiently, repeatedly, without interruption. If a modern human were placed here during that interval, survival would not be determined by temperature alone, but by mismatch. Lungs tuned for thin polar air would meet dense, humid pressure. Vision adapted for land would fail in suspended sediment and glare. Movement would be resisted by a medium that rewards anatomical streamlining over balance and grip. The mountain does not mark where predators climbed. It marks where continents traveled, where seafloor lifted, and where entire ecosystems were displaced upward by tectonic force. Predation, in this record, is not an event. It is a system property. These fossils are not out of place. The present landscape is. Warm, shallow marine carbonates do not form under ice. They accumulate where sunlight penetrates the water column, where suspended calcium settles through biologically active layers, and where microbial and planktonic production is continuous. The limestone encasing these predator fossils carries that signature in its crystal structure and isotope balance. Oxygen isotope ratios in the carbonate matrix indicate formation temperatures far above modern Arctic means. Carbon isotope excursions align with periods of elevated primary productivity, conditions capable of sustaining dense prey populations, and above them, large-bodied hunters with extreme metabolic demand. This was not a marginal sea, it was an energy-rich platform. Sediment texture reinforces the model. Fine-grained layering, low clastic input, and reef-associated microfossils point to a stable shelf environment rather than deep ocean deposition. Water clarity, nutrient cycling, and photic zone depth form the operating limits of the system. Every predator tooth found here is downstream of that energy geometry. A human body inserted into this environment would not read the danger correctly. The water would appear calm at the surface, yet below it, visibility would collapse within meters. Directional sound would distort. Escape paths would not be legible to a land-trained nervous system. The ecosystem functioned without observers, only gradients. Light, pressure, motion, determined advantage. Predator identity in this deposit is not inferred from size alone, but from tool geometry. Teeth recovered from these Arctic carbonates show recurved profiles, compression blades, and serration patterns optimized for tissue slicing rather than crushing. Edgeware under microscopy reveals repeated shear contact with collagen-rich prey, not shell. Function is recorded directly on enamel. Jaw leverage models derived from attachment scars and joint surfaces indicate rapid closure over endurance force. A capture strategy built on interception, not grappling. Vertebral articulation suggests high lateral flexibility, enabling burst direction changes in three-dimensional pursuit. This is the architecture of active hunters operating in open water columns, not bottom ambush zones. Encoprolite content and gut trace residues add another layer. Fragmented bone microshards and scale clusters show incomplete digestion, consistent with fast intake and competitive feeding pressure. Energy moved quickly through these bodies. Nothing about the waste profile suggests scarcity. Background fauna in the same strata, schooling fish analogs, armored swimmers, fast cephalopod forms, establishes the mid-trophic density required to support repeated apex feeding. Predator presence here is not anomalous. It is mathematically necessary given the biomass ladder below. A modern human entering this water column would misread distance and speed. Refraction shifts apparent position. Approach velocity doubles expectation. Reaction timing, tuned for air, lags behind hydrodynamic reality. In this system, detection failure is terminal, and detection delay is common. Movement in this marine system was constrained by physics long before biology added teeth. Water density imposed a constant energy tax on every trajectory change. Drag scaled with surface area and turbulence, rewarding narrow profiles, distributed muscle bands, and elastic recoil structures. Bodies that wasted motion did not remain in the upper trophic tiers. Fin aspect ratios reconstructed from attachment geometry indicate sustained cruising efficiency paired with short burst acceleration. Tailbeat frequency models place several of these predators in the high thrust category, capable of closing distance faster than most prey could reorient. The medium favored commitment attacks over prolonged chases. Pressure gradients added another filter. Even moderate depth shifts altered buoyancy and gas balance. And many active hunters show skeletal lightening and internal cavity distributions consistent with dynamic buoyancy control. Vertical maneuver was not optional. It was a survival axis. Ambient noise behaved differently than in air. Low-frequency vibration propagated farther and faster, turning muscle strokes and panic movement into detectable signals. Sensory systems evolved to read pressure waves, not silhouettes. Detection often preceded visibility. A human body placed here would generate excessive turbulence with every limb cycle. Kicking patterns designed for surface swimming broadcast rhythmic pressure pulses. Each pulse is range data for anything equipped to interpret it. In dense fluid, inefficiency is not fatigue first, it is exposure first. Evidence in this formation is layered, not singular. Fossil distribution follows bedding planes tied to specific depositional pulses rather than random scatter. Predator remains cluster alongside abrupt, faunal turnover bands. Intervals where multiple prey species appear and disappear within narrow vertical ranges. That pattern matches episodic ecological stress, not slow background death. Trace element mapping inside tooth enamel shows strontium and rare earth uptake profiles consistent with early diagenetic sealing, meaning burial occurred rapidly after loss. Transport distance was minimal. These hunters died inside the system they dominated, not far from it. The food web and the grave site overlap. Microfossils in adjacent thin sections, foraminifera and calcareous nanoplankton, function as temperature and salinity gauges. Their species ratios correspond to warm, shallow, fully marine conditions with stable circulation. The chemical envelope that supported the base of the food chain is independently verified at microscopic scale. Bone histology from associated vertebrae reveals growth ring spacing that indicates fast juvenile acceleration, followed by shorter mature intervals. A high-risk, high-intake life strategy, typical of active macropredators. Longevity was lower than mass would suggest. Throughput mattered more than duration. Introduce a modern human organism here, and none of these indicators signal danger. The water tests clean, the substrate looks stable. The lethal variables are dynamic, not visible. The record preserves outcomes, not warnings. The escalation point in this ecosystem is not a single species, but convergence. Multiple predator lineages show overlapping strike zones in jaw mechanics and swimming envelope, meaning pursuit space was shared and encounters were frequent. Competition pressure rises when hunters can intercept the same prey layers within the same depth band. Bite mark overlays on prey, fossils confirm repeated post-mortem feeding. Parallel gouge sets from different tooth geometries on the same bone surface. Carcass control was temporary. Kill ownership dissolved quickly into multi-predator consumption. Delay increased risk even for the attacker. Some skeletal remains show healed trauma, rib fusion, regrown fin supports, partially remodeled bite damage. Survival after attack occurred, but carried mechanical penalties: reduced flexion, the altered stroke symmetry, lower burst output. In a drag-dominated medium, minor asymmetry compounds into chronic energy loss. Population stability at the top tier therefore depended on constant replacement, not individual endurance. Apex status here is a throughput role, not a long tenure position. A human organism entering this escalation layer would interpret distance between threats as safety margin. In fluid pursuit geometry, that margin collapses quickly. Interception paths curve, not linearly approach. What appears separated in space is connected by vector math and momentum. At peak density, the hazard is not one hunter, it is overlap. The terminal layer of risk in this system is not predation, but environmental override. Sediment cores from equivalent strata show abrupt anoxic events, dark, organic-rich bands where bottom and mid-water oxygen collapsed. Such intervals form when circulation stalls and microbial respiration outpaces renewal. The food web above continues briefly, then fails in sequence. Sulfur signatures and pyrite framboid density in these layers indicate euxinic conditions. Toxic hydrogen sulfide rising into habitable zones. Gill structures optimized for high extraction efficiency become liabilities under poisoned gradients. Specialized hunters suffocate faster than tolerant scavengers. Dominance reverses without combat. Temperature excursions compound the effect. Rapid warming reduces dissolved oxygen while increasing metabolic demand. Growth ring compression in fish and reptile analog bones across these bands shows stress acceleration followed by sudden termination. The shutdown is systemic, not selective. No anatomical weapon counters chemistry at scale. Speed, teeth, and sensory range do not negotiate with altered solubility curves. Apex status offers no exemption from fluid composition. A modern human placed here would not detect the shift before impairment. Early symptoms, dizziness, confusion, motor error, would register as fatigue, not atmospheric change. By the time recognition forms, coordination is already degraded. In this latter, the final predator is not an organism. It is the medium itself. Failure in this environment follows physiology, not drama. Human muscle is built for intermittent load in air, where cooling is efficient and oxygen access is constant. In warm, mineral-rich seawater, heat shedding slows, while effort cost rises. Core temperature climbs as stroke efficiency falls. Fatigue arrives before distance is gained. Salt balance destabilizes next. Continuous immersion and accidental intake shift electrolyte ratios, impairing nerve conduction and muscle timing. Small coordination errors appear: mistimed kicks, incomplete breaths, delayed grip response. In a system where motion precision determines escape vectors, micro-error scales into capture probability. Vision degrades with depth and particulate density. Human binocular focus, optimized for air refraction, loses accurate range judgment underwater. Objects appear nearer and slower than they are. Strike timing models based on air experience become invalid. Reaction windows close unseen. Respiratory limits are absolute. Without specialized oxygen storage, usable dive time is counted in minutes, then seconds under stress load. Panic increases consumption rate, shortening the remaining window further. The constraint is chemical, not psychological. Nearby predator fossils show expanded rib cages and vascular channeling consistent with high oxygen throughput and buffering capacity. Their baseline operation exceeds human peak output. This is not a skill gap, it is a hardware gap. Death here is not violent by necessity. It is mechanical, the predictable endpoint of mismatched exchange rates. The fossil record at this Arctic elevation does not describe a tragedy. It describes a transfer function. Energy entered through sunlight and plankton, converted through layers of flesh, and terminated in bodies built for interception. When tectonic uplift displaced the seafloor, the system did not fail. It relocated into stone. Plate motion rates reconstructed from magnetic striping and radiometric dating show lateral transport across thousands of kilometers before uplift. The predators did not migrate to the mountain assembled beneath their graves. Compression, folding, and vertical thrust raised carbonate shelves into polar air over geological intervals far longer than any lineage survival span. Structural deformation in the rock, tilted bedding, pressure solution seams, in recrystallized veins, records the force pathway of that lift. Fossils remain oriented to original seabed planes, proving they were not redeposited by flood or slide. The ecosystem is preserved in operating position, only re-elevated. This reframes threat hierarchy. Individual hunters dominated momentary space, but lithospheric mechanics determined final position. Biological victory has no authority over crustal motion. Insert a modern human anywhere along that timeline, and adaptability still loses to rate mismatch. Evolutionary adjustment requires generations. Plate velocity requires none. The longest survivor in the sequence is not the fastest organism, but the slowest force. Extinction in marine predator lineages rarely appears as a single terminal horizon. Instead, the strata show stepwise thinning, reduced specimen frequency, smaller average body size, interrupted growth rings, and increased juvenile mortality signals. The decline is statistical before it is absolute. Apex presence fades before it vanishes. Prey layer indicators shift first. Scale assemblages become dominated by smaller-bodied species. Shell thickness decreases. Defensive morphology rises while total biomass drops. Energy throughput narrows. In such conditions, high-performance hunters become energetically non-viable, even while still anatomically superior. Isotopic stress markers inside late-stage teeth, especially oxygen variability across growth bands, record unstable seasonal chemistry. Oscillation replaces equilibrium. Predators built for consistent gradients encounter fluctuating ones. Optimization becomes rigidity. No layer records protest or struggle. Replacement species appear above, slower, more tolerant, lower demand. The system does not mourn specialization loss. It rebalances around efficiency under constraint. A modern human observer, if present, would not label this moment as collapse. Surface activity would remain. Water would still move. Organisms would still feed. The failure is invisible without measurement. Extinction in this record is not an event line. It is a declining equation. Modern interpretation adds instruments but not immunity. Remote sensing, isotope mass spectrometry, and synchrotron imaging can reconstruct temperature curves, diet ratios, and growth velocity from mineral traces thinner than a hair. Measurement expands resolution, not dominance. The observer remains external to the system described. Energy budget modeling applied to these predator anatomies shows margins narrower than intuition suggests. Even apex forms operated close to intake thresholds. A small prey density drop or oxygen reduction pushes the model into deficit within short time windows. Control was always conditional. This reframes biological power as temporary alignment with parameters, not superiority. When parameters drift, morphology becomes outdated faster than it can adapt. Selection does not negotiate with prior success. Human technology would extend observation time in that ancient sea. Sensors, rebreathers, armored shells, but each layer adds failure points and supply dependence. The organism is replaced by a logistics chain. Remove resupply, and exposure returns. Across the rock record, the consistent pattern is constraint first, adaptation second, disappearance third. No exception layer is documented. The system never required a witness to function, and it does not record approval.